This tutorial will discuss the types of shear wall design available in ETABS, as well as describe the capability that exists to optimize shear walls for drift. We will start by illustrating the three types of shear wall design in ETABS. First is the simplified compression and tension design, which designs planar walls. Next is the uniform reinforcing approach, which can design or check 3D walls using uniform reinforcing patterns. This is the default design. And last is the general reinforcing option, which can design or check 3D walls using arbitrary reinforcing patterns defined in the Section Designer program. The shear wall we will design is 1 story tall and 10 inches thick. However, before a wall can be designed, it must be assigned a pier label. Select the wall and go to the Assign Shell Pier Label command and assign a label, in this case P1. We can now run the analysis. With the analysis complete, we are ready to start the design. Select the wall and go to the Design Shear Wall Design command. Next, go to the Assign Pier Sections command, and here is where we select which of the 3 types of wall designs to assign. We will start with the simplified compression and tension approach. With the wall still selected, go back to the Design menu and select the View Revise Overwrites command. Here we verify our design parameters. Note that T and C is selected and that the wall is 10 inches thick. And if we wanted to, we could define edge members using the dB dimensions for both the left and right sides at the bottom and top. We are now ready to start the design. The required longitudinal reinforcing is displayed on the wall. A right click brings up a detailed design sheet showing flexural, shear, and boundary check information. Select the wall once more, and again go back to the Assign Pier Sections command. But this time select the Uniform Reinforcing option. In the form, you can specify the distributed uniform reinforcing and the end bars, as well as whether the wall should be checked or designed. We will select the checked option. If we select the wall and go back to the View Revise Pier Overwrites command, this time the form displays uniform reinforcing as the type, the reinforcing we selected, and that it is a check. Next, we rerun the Design Check command. And the total longitudinal reinforcing specified is shown. A right click brings up detailed information on the check, including the demand capacity ratios. If we wanted to display the DC ratios on the model, we can do so using the Display Design Info command. Next, we will use the General Reinforcing option. However, prior to assigning this type, we must define the section using Section Designer. This is done through the Define General Pier Sections command. We will add a new pier section but we will base it on the existing P1 wall pier geometry. Click on the Section Designer button to edit or modify the section, including right-clicking on the reinforcing to bring up a form where we can change the size and spacing as needed. When the changes are complete, click on the OK button. Now we can assign the Section Designer section to the wall by selecting the wall and going to the Assign Pier Sections command and choosing the General Reinforcing option. Highlight the section we defined for both the bottom and top and make sure that the checked option is selected. If we go back to the View Pier Overrides command, note how the form has changed to reflect our current design choices. Once again, start the check of the wall. The total longitudinal steel is shown. A right-click displays the design form, including the demand-capacity ratios. As a last step, select the wall and change from checked to design for the general reinforcing choice. Start the design again. And now that the program is doing design rather than checking, it displays the required longitudinal reinforcing rather than the reinforcing that was specified in the section designer. One other powerful feature that ETABS offers when designing shear walls is the ability to select the thinnest wall section that satisfies lateral drift requirements. The section is picked from an auto-select sections list that the user creates, similar to what is done in steel and concrete frame design. We start by going to the Define Section Properties Wall Sections command. Here we have previously defined 7 wall sections ranging in thickness from 6 inches thick to 18 inches thick. Clicking the Add New Property button, we will name this property Auto Select and choose a property type of Auto Select List. When this property type is selected, the Modify Show Auto Select List button becomes active. Clicking on this button, we will add our 7 wall sections to the Auto Select list. Note that our starting section is the median property, which in this case is wall 4, which is 12 inches thick. Next, we select the wall and assign the Auto Select property just defined. Note that wall 4, the median section, is shown on the display. Next, we will set the lateral drift target by going to the Design Set Lateral Displacement Targets command. Here we set the maximum displacement at the top of the wall to 1 inch for our lateral load case. We are now ready to run the analysis. And once the analysis is complete, we can move on to design. A check of our peer overwrites shows that design using uniform reinforcing has been selected, which is the default and typically what should be used with auto-select lists. We can now click the Start Design command. And after it is finished, a right-click shows that the median section, the 12-inch thick wall, has been used for the first cycle of analysis and design. A check of the displacement shows an X translation of 0.57 inches, significantly below our target of 1 inch, and therefore a thinner section can be used. The section thickness will not be adjusted until we rerun the analysis. After running the second analysis, the wall section has been updated. It now uses wall 2 as shown in the display. Wall 2 is our second thinnest section, 8 inches thick. We will now rerun the design, and the required longitudinal steel for section wall 2 is displayed. A check of the displacement shows that the X translation has increased to 0.86 inches using the thinner section. This is still below our maximum of 1 inch and thus is an acceptable section. This concludes this watch and learn on shear wall design.